All right, so this will be a real quick video. I'm just going to take one of the examples that were in the slides, write it as linear, in matrix form. So here's a system of equations, and again, this thing is always out of focus. Let's get this thing in focus. There we go. And we'll take this system of linear equations, write it in matrix form, and then we'll solve it in Matlab, okay? So not too hard, okay? All right, so here we have three equations, and we have the three unknowns, x, y, and z. So the first thing to do is to get that into matrix form. Obviously, you can do this just by direct substitution or Gaussian elimination or something like that, but in this class we'll be using Matlab quite a bit. We'll be dealing with bigger systems of equations, and so it'll be quite useful. So let's do that. So we have our variables x, y, and z, and three equations. Okay, so the first thing we're going to do is get all the variables onto the left side, x, y, and z, and then all the other terms, terms that don't involve x, y, and z onto the right side, okay? So let's take this first equation. So, well, look, you got a 3. If we bring that over to the right side, that's a minus 3. All right. We got a minus x on the left side, a plus y, and then if we bring the z over to the left side, that's going to be a minus z. So there's that equation. You could also multiply it through by minus 1, and I don't know, makes it x minus y plus z equals 3. Obviously, those are the same equations. You can use either one. Maybe the second one looks a little nicer. It's got less minus signs, whatever. All right, we do the same operations to the second equation. Again, moving all the terms involving x, y, and z onto the left side. So that's going to give me 3x minus y equals 0. Okay, so that equation is a homogeneous equation because the right-hand side is 0. The first equation is inhomogeneous, okay? And then again, doing the same thing with the third equation. So let's call this will be our first equation. This is my second equation. And then finally, the third equation is going to be minus x plus 5y minus z equals 0. And again, if you want to multiply by minus 1, that's fine. You get x minus 5y plus z equals 0. And that is the third equation. All right. So now we have those pretty much set up to go. So now we need to write our matrix form. So here we go. The coefficient matrix, or in this class we're going to be calling this a stiffness matrix, is going to be a 3 by 3, right? And that's going to get multiplied by the unknowns. So that's going to be x, y, and z. And that's going to equal the right-hand side. All right? Now, the first row multiplied by the unknowns equal to the right-hand side is the first equation, right? So the first row is going to be equation 1. The second row is going to represent equation 2. And the last row is going to represent equation 3. And, same here on the rows of the matrix. Now, if you think about columns, well, when you multiply a matrix by a vector, basically you're taking the row of the matrix and you're dotting it with the vector. So this first column is going to be the coefficient of the x term. All right? The second column is going to be the coefficient for the y term, and the last column is going to be the coefficient for the z term. Right? Now, obviously, the right-hand side vector is going to be what's on the right-hand side. So for the first equation, let's do that. That's the easy part. On the right-hand side, for the first equation, we have a 3, right? So that's going to put a 3 there. For the second equation, on the right-hand side, we have a 0. And likewise, for the third equation, on the right-hand side, we also have a 0. All right, so now, again, first row is going to be for the first equation, right? So here is our first equation. The coefficient of the x term, or the number that gets multiplied by x for the first equation, is going to be a positive 1. For the second column, this is the coefficient of the y term. So here you can see it's a -1, right? And then finally, the coefficient to the z term, and that's going to be a +1, right? So you can take this row, dot it with the column vector x, y, z, and see that that recovers the first equation. So 1 times x is x, -1 times y is -y, so x minus y, and then finally plus z equals 3, and that's the first equation, right? So remembering each one of these columns, although they just look like columns in a matrix, they actually have a meaning. They're influence coefficients or weights for the unknowns in the system of equations, okay? So now let's do the second equation. 3 is the weight for x in the second equation. For y, we have a -1. And for z, there's nothing. So it's a 0. 0 times z, right? And then likewise, for the last equation, we have 1 -5, 1. So this is now going to be our system of equations. You know, sometimes people write this as an A matrix or B matrix. It doesn't really matter for us. In this class, we're typically going to call that K. This one here is X sometimes, or Y, it doesn't matter. For us, these are going to be what we solve for, and we will typically call that D. And then finally, on the right-hand side, we're going to refer to the right-hand side vector as F, okay? All right, so we've written the system of equations in matrix form, and now we want to find the solution, right? And this is going to be D, right? Because that's basically going to give me X, Y, and Z, the solution, right? All right. So again, when these system equations get more complicated, it's going to be difficult to do these by hand. So something like Matlab is a great tool for this. So here I've got Matlab loaded, and hopefully the fonts are big enough that you can see at least what's going on in here. So actually it's pretty straightforward, right? So mostly you're going to be working in this command window here. If it's set up normally, the default is you have this nice little workspace over here on the right that allows you to see what variables you've defined. Right now we have no variables defined in memory, so there's nothing listed here. And here's where we put our operations, and you see the feedback. Later on, we'll also use script files and function files to kind of automate some of this work, but for now, let's just assume you haven't really seen too much MATLAB and just keep it simple, okay? All right, so the first thing we want to do is define the matrix K. So the process we're going to do here is we're going to define the matrix K, then we're going to define the right-hand side vector F, and then we're going to solve, or ask MATLAB to solve it, using a factorization scheme, actually, for the displacement, for the unknown vector D, all right? So let's first define the stiffness matrix. So we're going to give the variable K. That seems to make sense, or I should say the linear system matrix, all right? So you would type this in pretty much like you would see it, all right? So in MATLAB, when I use a square bracket, this means that we're going to define a matrix in here, okay? And so we enter the matrix in row order. So what we'll do first is the first row, and then there'll be a semicolon to denote that we go to the second row. We'll put in those values, and then another semicolon to denote the end of that, and then finally the third row. Okay. So for us, I know I'm blocking it, but you know, you can probably, hopefully you wrote it down. Maybe, I don't know if I can get both on here at once. Well, okay, there's the matrix. So remember it, right? But we'll go back to it. So the first row was 1, -1, and then 1. A space is fine to break up elements of a row. You can also use a colon, a comma if you want, that's fine, okay? Now that's the end of the first row. So we use a semicolon. That means now we're gonna enter in entities for the second row. So that'll be 3, -1, and 0. And then likewise for the last one, 1, -5, and 1, all right? And then we hit enter. You can see actually when I move the cursor over the close bracket, it gives me a little syntactical check that, you know, that defines the matrix. Spaces anywhere is fine. You can have extra spaces here. You can mix spaces and commas. It doesn't really matter. So, okay, so now I'm going to hit enter. And now you can see it spits back the matrix, and you can check that it's the same as what we had on paper. And also, if you look up here, I'm blocking it, but if you look up here, it has the variable defined in the workspace. Okay, so you know it exists. All right. All right. Next, we have to do the right-hand side. So this is going to be my F vector. You know, everything in Matlab is a matrix. So, in fact, a column vector is really a 3x1 matrix. So we define it in the same way. So for us, remember, that is 3, 0, 0, right? But each one is a row. So it's going to be 3, semicolon, because it's a second row, 0, semicolon, and then 0, right? Square bracket, again, to close off and say that we're finished defining this matrix. In this case, it's a column vector. Hit enter. So now I've got K and F in memory. All right, so now what's the syntax to actually solve this? All right, let me just go back to the piece of paper. I think it's kind of useful. I need another piece of paper, maybe, before I do that. It's a good thing you don't see my office in this video. All right, so here's the Matlab syntax for solving, okay? So all right is KD equals F, but really this is the syntax for any sort of linear algebra solve. If you think about it, what would we do normally? So you got a matrix multiplied by a, well, let me do it. Let me not use this. Squiggles, let's write it like this, right? All right. So one thing you might be tempted to do is, in fact, multiply by K inverse, right? Which will give me K inverse K times D equals K inverse times the right-hand side. So I multiplied both sides by K inverse, you know, assuming we can find K inverse. And actually in Matlab, you can find the inverse quite easily. In Matlab, you're just going to do a built-in function inv for inverse, and then you just put in the variable you want to take the inverse of. So in this case, it would be the K matrix, right? So actually, if we were to jump back to Matlab, you could see that we could do something like that. If I do inverse of K, there it is. That's actually the inverse of K. All right. So, you know, for small matrices, this really doesn't make much difference. But when you solve very large systems of equations, you never, ever, ever want to compute the inverse of a matrix if you do not have to. It's a very expensive process and a very time-consuming process. In fact, the preferred way to solve a linear system of equations is to do something like either a elimination or a factorization type of method or an iterative method. Okay, they both have their pros and cons, and we'll talk about that a little bit later in the class when we talk about solving systems of equations. So in fact, you really don't want to do this, although you could do this in Matlab. Okay, you could solve for the inverse, call it like K inverse or whatever equals, the inverse of K, and then multiply F by that, and you would have the solution. Okay, but instead, imagine K, D, and F are just quantities, right? So if you wanted to solve for D in some sense, using this sort of abstraction, it would be F over K, right? Or, 1 over K is K inverse using, mathematical notation, right? All right. So in Matlab, this is what they want you to do. And so in Matlab, the notation's actually going to be as follows. D equals K, and then we use this backslash, I think that's the backslash, F. And so you can see, although that looks like a weird notation, you can see that actually is trying to imply F over K, or K under F if you want, right? And what this does is it doesn't find the inverse, but it does, it uses LUPAC routines to very efficiently solve for D, or solve this linear system for D. Most likely it's using like an LU decomposition, okay, or if it's symmetric, a Cholesky type of decomposition, okay? So it's much more efficient. So that's what we're going to do. Now, why the backslash? This is because we have the system written as a matrix, times a column vector equals a column vector. Another type of system you could have is a row vector multiplied by a matrix equals a row vector. And if you have that situation, so since these are column vectors, we use that syntax, okay? If it's a row vector, right, if we're trying to solve for a row vector, then the syntax we would use here is D equals F over K, which I guess maybe is what you would think it should be to begin with, right? So the reason why it's front slash or backslash has to do with whether your right-hand side and your solution vector are row vectors or column vectors. Like most often in this class, D and F are going to be column vectors, so we are going to be using this syntax, okay? All right, so let's go back to Matlab and do that. That was a lot, just to show a very simple bit of syntax. So now we want to solve for D. Oops, can't see it. Let's bring this back up here. So here we got D equals K under F. And I'm putting spaces here just to space out so you can see a little bit better, but obviously you don't have to do that, right? And then when I hit enter, now there's a D vector defined. This is it. This should be our solution. So basically, X should be 0.25, Y should be 0.75, and Z should be 3.5. If you want to check this, obviously it needs to satisfy the equation. So K times D minus F better be 0, and there it is. Sometimes it's not exactly 0, but small numbers. So you might want to say, is it close to 0? So we would use a norm, like the L2 norm, which is basically the same as the Euclidean length of the vector. And so you could take the norm of this matrix, I'm sorry, the norm, or which is the residual, right, of KD minus F, and here you can see it's 0. Okay, so it satisfies it. Okay. We can do other operations on K. If you want to figure out the determinant of K, it's just DET, and then operates on K, and here we got a determinant of negative 12. All right, remember, if the determinant is 0, that means you have a singular system. So let's do another matrix. Let's call A that is singular. So if you use the matrix 10, minus 10, 0. Oops, why am I doing that? Oh, I screwed up. There we go. 10, minus 10, 0, minus 10, 20, minus 10. And then finally for the third row, you know what? I screwed this up. Hold on a second. Forget this. I'm just going to hit it. Let's redefine A. Get that for A. A is equal to 10, minus 10, 0. That's the first row. Second row is minus 10, 20, minus 10. And then the third row will be 0, minus 10, 10. Okay? So this is a singular matrix. All right? If you try to find the inverse of this, it'll tell you it's singular. Right? It says, warning, matrix is singular to working precision, excuse me, means that there is no inverse that exists for that matrix. That also means that there's no unique solution, as we'll talk about in some other videos. So you couldn't solve, like if we wanted to solve x, you know, let's say we want to solve for another d using a instead of k, right? D equals a under f, it'll give me an error. It'll say that, you know, it's singular, can't solve that system. And again, if you looked at the determinant of a, you'll see that it's 0, right? Which means it's singular, okay? And that's because we actually do have a linear dependency here. If you look at this, if you take the first row and add it, and take the first row and subtract the second row, and you will get the third row. So the third equation is the first equation minus the second equation, basically, okay? So there's the linear dependency. All right, so that's the basics of it, right? So you should be able to take a system of equations, write it in matrix form, and then be able to solve it in Matlab, okay?